Hello, I'm Patrick MacArthur. I'm a PhD candidate at the University of New Hampshire, and today I'm going to be talking about urdma, which is a RDMA software emulation using DPDK. This is a project that I started while I was an intern with IBM Research and has since been open sourced. And I'm continuing to use it as the vehicle for my dissertation work. So basically, I just want to give a fairly high-level overview, some background stuff, talk about the implementation, talk about some of the issues that I've encountered using DPDK and how I worked around it, and give a little bit of a performance evaluation. So for those of you who don't know about RDMA, I'll give a brief overview. So RDMA is commonly used in HPC. It provides a zero-copy kernel bypass. It's at a higher level than DPDK in the sense that it works with application messages as opposed to just at the packet level. And it can do zero-copy transfers between arbitrary virtual memory regions, assuming that they have been pre-registered, which requires that you have specialized hardware that can do that address translation. It has an asynchronous API called the verbs API that provides several different types of transfer operations, including being able to directly push or pull data from remote memory. There are several different RDMA standards. The one that urdma implements is iWarp, which is a protocol that the IETF made that runs over TCP/IP. So urdma is a software emulation of RDMA to be able to use RDMA on commodity Ethernet NICs that can run DPDK. And its goals are to have reasonable performance and to be able to run unmodified verbs applications and to perform all data transfers in Userspace. And where this differs from prior work, such as soft iWarp and soft Rocky, is that urdma performs its data transfer in Userspace as opposed to existing solutions that perform the data transfer in kernel space using the kernel sockets API. So urdma enables easier development in the sense that user space development is easier than kernel space development. And it also is useful for storage applications in the sense that it will allow easier integration with SPDK. So looking at the implementation, so it's implemented as a multi-process application with a kernel module. The kernel module is required for connection management support in addition to verbs initialization. The RDMA verbs APIs require that the kernel exposes a device in order to initialize. And then it has a primary master process that does all of the setups, and then a provider library that performs that implements the verbs API and does all of the data transfer. So the protocol that urdma implements is the top level of the iWarp protocols, but it implements it over UDP for reasons of simplicity. And I implemented a very simplistic reliability shim over UDP to just get the minimum protocol to implement reliable messages. So how the packet processing works. So the master process base assigns each RDMA queue pair a hardware received and transmit Ethernet queue. And this allows verbs applications to access the NIC independently of each other. without the need for any other synchronization. And I use the Ethernet NIC hardware receive filters to separate the packets to the appropriate receive queues. Currently using the flow director and tuple filtering mechanisms. All unfiltered packets are sent to the master process, and then they go to the kernel via KNI to allow the kernel to receive connection management packets, which are processed by the kernel. And I'll get into how the connection management works in a bit. For filtered packets go directly to the appropriate process to be processed as part of whatever RDMA queue pair they were intended to be used by. So so one of the biggest issues that I encountered was with DPDK initialization, and there was and the presentation yesterday talked about a lot of these issues. But one of the big points that bears reiterating is, as a verbs provider library, I want DPDK to essentially be invisible to the user verbs application. It should just feel like any other verbs provider. So hence we call the RTAL init function in our own implementation. And so the issues that were brought up yesterday with RTAL init, like it taking command line arguments, it changing the CPU affinity of the calling thread, are issues of our implementation of urdma. urdma works around this by spinning off a separate thread to call RTAL init. And using that thread that it spins off, that becomes the master L core, as simply a background progress thread. One of the other issues is all verbs applications must run as the same user. That user does not necessarily have to be root if you're using VFIO, but that they still have to run as the same user. So the data transfer phase, the data transfer, as I mentioned, is done by a background progress thread. This thread separates DPDK operations from application threads. It allows all of the caching APIs and everything to work. And it allows the progress for RDMA read and RDMA write operations to occur outside of application verbs calls. And I simply do the inter-thread communication via ring queues, and I try to do that in an efficient manner of dequeuing entries in bulk. Connection establishment is the other interesting thing, is making sure that we get the hardware filters set up before the connection is established and the application starts making verbs calls. And because there's so many different things that have to interact here, basically when the application calls RDMA connect, that goes into the kernel. The kernel is the one that actually does the connection management packet exchange. Once it actually decides that this is actually going to be a connection, it sends our kernel driver sends a message to the DPDK master process telling it to set up the hardware filters. Once those are set up, it sends a message back to the kernel module telling it that it's okay to send the established event back to the verbs application. And this exchange needs to happen this way to ensure that the receive filter is active before the first packet arrives. So next, I'm going to just look at performance evaluation. So this performance evaluation was done a little while ago. And I'm basically comparing urdma against a reference iWarp hardware solution, which is just a Chelsea iWarp NIC. And so for this performance evaluation, basically I'm just using the Chelsea Nix as the base, as kind of the ideal, and not expecting URDMA to necessarily reach that, but just as kind of the ideal point. So for latency, the latency here, lower is better. So URDMA has about double the latency of the Chelsea RNIC so not entirely unexpected. Ideally, the latency will get better as I continue to improve it. The RDMA read latency looks worse because it's of the fact that in RDMA read, the data arrives in the opposite direction as the requests. So it's measured as a round trip operation, whereas the other two operations, the data goes in the same direction as the request, so it's measured as a one-way. Throughput-wise, URDMA for the RDMA read and RDMA write operations perform much closer to what can be achieved with the hardware. The send-receive, there's some issues because that's a two-sided operation, and the queuing, that there's some inefficiency that causes the throughput to be a little less than what we would expect to see. But for the RDMA write between like 4K and 1 megabyte messages, we get pretty decent throughput. So to summarize, URDMA is a software emulation of RDMA to run unmodified verbs applications. And unlike previous solutions, it's a hardware agnostic solution that performs all of its data transfer in Userspace. And it achieves reasonable throughput. So there's some future work here. One thing is that it would be ideal if I could manage to achieve zero copy sends. Using URDMA for NVMe over Fabrics traffic, using SPDK to do zero copy transfer between the storage device and the NIC, and integration with storage class memory. So with that, thanks for listening. I'd be happy to answer any questions, and I have my contact info and the download for URDMA. Yeah.
So in future work, you didn't mention any standard wire protocol, iWarp or RDMA like the Rocky. Is that planned also?
So URDMA implements iWarp currently. Currently, I don't have any plans to have it implement Rocky, but because that was basically just a design decision that was made early on.
And just another question. You have a separate thread that does the data copy instead of the application thread, where hardware would have done it otherwise, I guess. So what's the big advantage compared to the kernel, for instance, the soft Rocky? Because over there's a kernel thread that does the data copy, and you have a single data thread that's going to block when you scale.
So yeah, I guess in this sense, the advantage here is that it being based on DPDK allows the data transfer to be a Userspace implementation, and the Userspace and just in the sense that that may be a more like an easier way for people looking to develop new RDMA features, or like as like a prototype implementation, for instance, might find it might find it a little easier to get started with a Userspace implementation in terms of like the debug environment and so forth, than adding it, then trying to, for instance, extend soft Rocky and having to actually write kernel code.
So Thank you, Patrick. If there's any more questions, maybe we'll catch up offline. Thank you.